Hey guys, welcome back to another exciting episode, episode 3 of Awesome Sexy Math. Oh, that's right, this just isn't awesome math, it's awesome sexy math. Woo! Okay, I thought about that. I think it'll get embarrassing. I'll either get numb to it, and it'll just be, it won't have any effect, or it may just be, continue to be odd, but whatever. Okay, so Pascal's triangle. This is so awesome. Oh, I love math. Oh, math is awesome. Okay, so Pascal's triangle. Last episode, we talked about the inscribed vertices on a circle, remember? Each row of Pascal's triangle was the number of vertices, and then the number of segments, and then the number of triangles with segments, and then the number of segments and triangles and quadrilaterals, and then you add on pentagons and hexagons, heptagons, octagons, all that stuff. That was just one row of Pascal's triangle. Well, guess what? There's like 10 patterns. 10! All hidden away in Pascal's triangle, okay? Now, as usual, I'm just kind of winging this, but it's all true. Now, I'm going to left justify Pascal's triangle, okay? I'm going to left justify this. This is the same Pascal's triangle, but it doesn't have that same symmetry. It's all left justifying, okay? Now, alright. Okay, so that's good enough for there, right? Now, this is where things get really awesome. So let's take that. Let's take that. Let's take that. And now let's take that. Now, all of those add up, okay? So this is, what's 1 plus 0 is 1. This is diagonal, okay? So that's 3. We're diagonaling these, summing the diagonals, okay? So that's 5, 7, 4, 1, 4 is 3, that's 8. And what's occurring here is that is the Fibonacci series. The Italian mathematician. That's the Fibonacci series. And if you continue going on with Pascal's triangle, then you see more of these. I mean, you see the rest of the Fibonacci sequence. That's amazing! Oh! Pascal's triangle, math, Fibonacci, that's awesome! Woo! That's so cool. That's like hidden away in Pascal's triangle. It's like this secret in Pascal's triangle. In 1996, I read this 2,000-page book on computers called Secrets. And I was learning about all computer stuff working. That was kind of cool, but this is like even more impressive. This is the most amazing thing. This is so awesome. Okay, now this one is awesome. I was so psyched about this. Why? Because when I'm bored or when I want to focus, or a lot of times when I feel scared, or when I feel kind of like concerned or out of it or perplexed or something in life, I do powers of 2. 1, 2, 4, 8, 16, 32, 64, 128, 2, 5, 6, 5, 12, 1024, 2048, 4096, 8, 192, 16, 384, 32, 768, 65, 536, and I go back down. I don't want to do them again, but check this out. When I saw this, I have to do it, I have to go all the way back down. It's like that. 65, 536, 32, 768, 16, 384, 8192, 496, 2048, 1024, 512, 256, 128, 64, 32, 16, 8421. Great. Hey, Pastor 2E. Now this is awesome. If you add up each row, you get the powers of 2. Each row is the power of 2 to that row. What is 2 to the 0? 2 to the 0 is 1. What is 2? Oh, you know, there should be a 1 here. Bloody hell, whoops. Oh well. What is 2 to the 1 is 2. What is 2 to the 2? This is the second row, third row, fourth, fifth, sixth, okay? Bloody hell, this is kind of sloppy. Hey, pass for 2E. That 2 to the 3 is 8, right? That's 6, 7, 8. That equals 8. That equals 4. You see, we're summing these rows, right? What is the sum of this row? Well, 10, 14, 16. And the sum of this row is 32. The sum of this row is 64. Isn't that awesome? That's so awesome! Woohoo! When I saw this, I was like, I rarely have like jaw-dropping things, but that was awesome. That was seeing jaw-dropping things. That was so cool. These rows of Pascal's triangle. Yes, there are the amount of inscribed things in the circle. Inscribed segments, triangles, quadrilaterals, segments, or vertices, segments, triangles, vertices, triangles, quadrilaterals, pentagons, etc. But it's also, the sum of those is the powers of 2. That's so like, it's not magical because it's crisp, it's precise, it's clear, it's math. It's awesome. Let me put plus 2 here. And that's so cool. That's so awesome. So we've got, right now we talked about inscribed circles, the inscribed vertices on a circle, right? We'll talk about Fibonacci. When I was in elementary school, I had this a French classmate who was named Thibaut. It was spelled like Thibaud, so we called him Thibaud. Funny. And there's no relation to the Italian mathematician Fibonacci. And we also have powers of 2. There's 3 awesome patterns in Pascal's triangle. There's 3, and there's 10. There's no way I'm going to do all 10. But that is 3. Now, let's do magic 11s, okay? Magic 11s is 11 to the n. Now this one's interesting. 1. And I thought about like pausing this and redoing the Pascal's triangle, you know, off camera. But when I do it on camera, oh bloody hell, that's sloppy. When I do it on camera, it reminds you just how easy it is to draw a Pascal triangle yourself. You don't need any equipment, and you can just kind of check this out with yourself. It's math and being aligned and clear and awesome. Okay. Now again, we're going with rows here, okay? Now, we aren't summing the rows. We're looking at each row as if it were a number, okay? And when something has more than 1 digit in the 10 spot, you carry it, okay? Oh man, my markers. Okay, so this is 0, the 0th row. This is the 1. This is the 2, 3, 4, 5. So that's the 0th number. In computer science, like most arrays start with 0. So this is the 0th. This is the 1th, the 1st, the 2nd. Okay. And this is 11 to the n. This is so awesome! Woo! 11 to the 0, the 0th power is 1. 11 to the first power is 11. What is 11 squared? It's 121. That's so awesome! What is 11 cubed? It's 1,331. You can, you know, multiply that out, or you can do a calculator or whatever. And what is 11 to the 4th? It's 14,641. Now this is where this one, because there's 10s, it's not, you know, it's not 1,510,105. You carry over the 10. So this would be, so 11 to the 5, using this row of Pascal's triangle. Now this is just like amazing connections with math. Essentially this might be useful on some kind of test or exam, but that's not why I'm edifying it, why I'm sharing it. It's just awesome. I mean, you could draw Pascal triangle rows to do powers of 11 without a calculator, I guess, or something. It might actually probably a lot faster than doing 11 to the 5th or whatever, just on paper, unless you memorize 11 to the 5th or whatever. Anyways, so this is that, and this is a 0, carry 1, 10 plus 1 is 1, carry 1, 1 plus 5 is 6, that. So 11 to the 5th is 16,105. And I'm just going to double check that. Yeah, when something is off, I usually have a pretty good sense of knowing when it's off. And this is on. Math is on. Math is awesome. Woo! I forgot the 1 there. So it is 161,105. 1 is 11 to the 5th, which is the 5th row of Pascal's triangle. This is so awesome! This is amazingly awesome. So we have all these rows of Pascal's triangle, all these patterns, okay? We've got Phibo, 2 to the n is the row. Phibo is the left justified diagonals. We've got inscribed in a circle, segments, triangles, quadrilaterals, pentagons, hexagons, etc. as each row. And then we've got 11 to the n as each row. That is just those 4 patterns. And we talked about the inscribed stuff yesterday, the previous episode, episode 2 of Awesome Sexy Math. And these are 3 new patterns that we've introduced. This is so awesome! This is so amazing! Now, where did this thing come from? Well, Blaise Pascal was kind of a philosopher, mathematician dude. He kind of noticed a lot of these patterns, but originally Pascal's triangle was derived by Chinese, which is awesome. And a lot of things come from China, most everything comes from China. China's awesome. Well, actually, I don't know. I like Chinese food. Well, I like Japanese food. Anyways, I like ethnic food, whatever. This is not about food, this is about math. Oh, math is awesome! So, yeah, that's so cool. I'm trying to think of any other pattern. Well, there's only 4 of the 10. And I think that's enough for today. So, yeah, enjoy the awesomeness of math. Whoa, math is awesome! Woohoo! Hey guys, welcome back. I really need to invest in a tripod. This is the final fifth pattern of Pascal's triangle. I drew it all out because I didn't want to do this on camera. It's just more precise. This is the hockey stick pattern. Okay, so this is 5 patterns that we've now covered. In my personal opinion, the 5 coolest out of the 10. It's probably even more than 10 in Pascal's triangle. We just talked about Fibonacci, which is left justified diagonals. That's what 2e. We talked about magic 11s, which is the row number of 11 to the n. We've talked about 2 to the n, which is also the row number, the sum of the row number. That's the row sum. We've talked about inscribed circle, which is the row number of segments, triangles, quadrilaterals, all that stuff. And this is the hockey stick pattern, which is the sum of diagonal equals the little foot of the hockey stick thing. Or it's a sock, or whatever, it's the shape. So here's what you do with the hockey stick pattern. Ooh, that was agile, Pastor, doing nice. From one of the edges, I mean, it has to start with a 1. You draw a diagonal of any length. Okay, so look at this hockey stick pattern. See that one there? So this has 1, 2, 3, and then the little foot of that is 6. The little foot always equals, I'm in this frame. Oh gosh. Need to get a little better, more high-tech tripod stuff. That would be a lot better. That little foot thing equals the sum of that diagonal. Isn't that amazing? That's so awesome! Oh, I love Pascal's triangle! Oh, I love math! Oh, there's a little bit longer one. 1, 3, 6, 10, 15. Sum those up. What do you get? Well, you get 35. It's so awesome! Here's another one. 1, 3, 6, 10. Sum of those. That's 10 plus 10 is 20. And any diagonal of any length, it'll always have the foot of that little sock or hockey stick or whatever, or I like sock, it looks like a Christmas stocking or sock, equal the sum of that diagonal. Now the only rule with that is it has to start from an edge. You can't just like do an interior diagonal. But just any diagonal of any length will always equal the little foot of that as the sum. So that's just another amazing thing. And these are 5 patterns of Pascal's triangle, which is so awesome. It's so cool. It's just like this simple mathematical triangle of numbers. There's also some more advanced stuff with like Sierpinski's triangle and stuff. We might get into that later, but I don't know. Those are just the 5 ones that are just so, like, awe-inspiring. I love this. This is so awesome. So, thanks again for tuning into Awesome Sexy Math. Be sure to subscribe to catch future episodes of math awesomeness. And there may be a lot of shows out there that are awesome. And maybe there's some shows that are sexy. And maybe there's some shows that are mathematical. But this is the only place to get awesome, sexy math. Woohoo! So, awesome.